Okay, so before we get started, right, everybody knows that midterm 2 is coming up. We put the announcements on the homepage. Most important bits, the rooms are different. The rooms are going to be slightly better than midterm 1, but still I couldn't get Walker because of 802. 802, of course, conflicts with our exam, and then, of course, they are bigger, and they get Walker. But pay attention to the room. Don't go to the midterm 1 room. So that's one thing. Second thing, some of you might be following Piazza and notice that there's a discussion about releasing lab answer keys. There's a back and forth, but the gist of it is that we've released lab takeaways. So if you were thinking about reviewing the labs, pay attention to all the past labs. There's going to be more text on the lab page. Just a heads up. So welcome back to lecture 9. Today we're going to talk about transformers, the pinnacle of modern-day deep learning architecture. If it needs any motivation, it suffices to say that T in ChatGPT stands for transformer. So it really is the architecture that spearheaded most of the recent advancements in language processing. And indeed, we're going to try to understand transformers from a language processing perspective. And in particular, we're going to start with a revisit of a concept that we introduced last time. We mentioned this idea of word embedding, how we can frame or turn raw words, English words, any language words, any language, natural language words, into a space, into a vector space. And we mentioned that word embedding, a good word embedding space, would be one that preserves semantic meanings. Things like dot product would encode similarity. So similar words would be mapped to a place that are nearby in this vector space, in this word embedding space. Similarly, directions in a good word embedding space would encode semantic meanings. So for example, here we see that the one direction encodes the leader direction, one direction encodes sort of Japan to Germany, right? So we mentioned that good embedding space vector spaces are the one that would be equipped with semantically meaningful vector arithmetics. And in particular, we looked briefly last time at this toy example of doing some sort of soft dictionary lookup. And if you recall, we coded up this dictionary, this trivial dictionary that has 3 pairs of English to French translation pairs, where well, we said, okay, we can code the translation into this key value tuples, and if we wanted to query our dictionary, the English word orange, what would be the French translation? Well, a dumb dictionary lookup such as Python's hard-coded dictionary would complain, but you and I, with our human intelligence, we could all nod along with this answer, somewhat still trivial of an answer that just merges together a bunch of French words, right? So maybe the French translation for orange, based on the available information given to us from this dictionary, would just be a merging, a 10% merge of the French translation of apple, 10% merging of the French translation of banana, and 80% of the lemon because, well, it's most similar to orange. And you and I alone would nod to this somewhat of a messy idea because you and I sort of put these English and French words not in terms of the words characters as Python would do, but rather we are thinking of these words really in terms of their meaning. In other words, we've already mapped these query key value, the raw natural language representation of these words, in some sort of a good embedding space in our human brain, such that when we do this kind of 10%, 80% of merging together or weighted sum of all those French words, well, we can make sense because of the similarity, right? Because the mixing percentages would make sense. And as we will see, the heavy lifting, the magical piece of transformer, the so-called attention mechanism, very roughly does exactly this process. In particular, in an attention mechanism, we're going to see over and over in today's lecture. And there are two steps, two main steps. First is exactly this type of dot product similarity comparison. We want to understand for a given query how similar it is to a particular key. So that is materialized or mathematically realized through this dot product similarity. And again, this hinges on the query key are already living in a good word embedding vector space. So first step would be dot product similarity. Then we would want to get some percentages. We want to merge together a bunch of values. So what is a tool that we're familiar with that turns some raw numbers into a distribution? Softmax. So we then would apply a softmax on top of some dot product similarity such that, well, we can get mixing percentages like 0.1, 0.1, 0.8. And these mixing percentages would then be used to weighted sum together all the values. And of course, this idea, this whole pipeline of doing some similarity comparison, squash that into some percentages, and then use those percentages to merge together a bunch of values, those are, of course, at a high level, very intuitive, very agreeable. But then much of the discussion today is going to be looking at how we can automate this process into a mechanism, into a machine. So towards that, we're going to follow this agenda for today. We're going to start with an end-to-end overall review or overview of the transformers architecture. Then the majority of the lecture is going to be spent on understanding these key pieces of attention mechanism. Later, we're going to generalize the attention mechanism to talk about something that's called multi-headed attention. It basically copies attention multiple times. And towards the end, as we did last time, we're going to introduce some of the recent ideas emerging from the research field. So if you recall, last time we already sort of got a glimpse of the transformers idea, right? So we mentioned large language models, they are trained in this self-supervised way where the engineering team from the companies developing these models, they would just copy, download the whole internet as is, download the text as just some unlabeled data. Then we would cook up some supervised or pretext task such that we could turn these unsupervised tasks into some supervision or into some sort of target that we would want to predict. In particular, suppose the team download this word, this full sentence from the internet. To date, the cleverest person or the cleverest thinker of all time was Isaac. So how do we turn this unsupervised bunch of raw text into some sort of supervised data set? Well, we would iteratively hide part of the sentence and use the rest of the context as the feature and try to predict iteratively what's the next word. So we would cook up this features and labels pair to assemble us a training data set. And our goal, or the model's goal in the middle here, is to append the prediction of the next token to the previous feature and iteratively, continuously try to finish the thought or finish the whole sentence in the so-called auto-regressive way, auto in the sense of, you're doing some sort of a self-bootstrapped next word prediction. So the first step of doing this mechanically is always to chunk up your feature into small bits. And these bits, for now, you can think of them as words or punctuation or some small pretext or some prefix of a word or suffix of a word, small bits of the word. And the first step is the so-called tokenization step, which exactly is the embedding idea that we talked about last time. So you could imagine just download a large language model, a pre-trained model from the internet, similar to the ones that you downloaded from Homework 8, right? So you could download from the net a large language model, plug in some raw words, natural words, and the model is going to return to you some vector representation, those semantically meaningful vector representation. So this step is called input embedding. Suppose we have a sequence of n such small chunks. Each of those chunks is going to have the mapping done into a d-dimensional space. So this d-dimensional space, we're going to encounter it over and over in today's discussion. So d-dimensional is always the word embedding space. And typically, d-dimensional space is a high-dimensional space because, well, we're encoding all of these words, these raw English words, whatever, into this vector space. So this vector space has to be very rich to capture, say, all the nuances of raw English words. There are a lot of raw English words out there, so you can imagine how this D has to be high-dimensional. So for reference, GPT-2, which is a relatively small model, has a D that's a 768, which you also encountered in your homework. The numbers don't really matter, just the magnitude, right? So it's high-dimensional. In GPT-3, it's already increased to 12,000. So in now modern day, the theme of the trend is really just go bigger and go deeper. So this number could be a very big number. But the first step, you can think of it as a trivial lookup table, where we download a model, plug in some words, turn that into some vector representation. Once we have these vector representation, or so-called tokens, each token really is just a transformer's jargon way of talking about vector, then these whole sequence of vectors or tokens is going to be passed along layer by layer. First, through this so-called attention layer, then something familiar, the multi-layer perceptron or fully connected feed-forward layer. You see that, pay attention to how attention layer does these arrows that's kind of parallel, right? So attention layer does these kind of horizontal back and forth of arrow, right? There are some values updating internally, and then multi-layer perceptron, it's each neuron or each token updating on its own. We're going to describe in detail of what are each of these steps doing, but at a high level, through this whole pipeline of attention layers stacked together with some multi-layer perceptron and repeated multiple times towards the end, the word embedding that d-dimensional space representation of the last word is going to become a new number or a new vector. And at the very last step, that whole vector representation is going to be reverse mapped into a distribution over dictionary. And our hope is that while a well-trained transformer, through whatever internally trainable weights or internal knobs that we turned, would be one such that through this whole processing, the last token's representation would give rise to a distribution in which the correct next word is assigned high probability. Does that high-level intuition make sense, right? So you have some given words, you have a sentence, you chunk that up into small bits. For each of these bits, you have a d-dimensional representation that through layer by layer, through the so-called transformer block by block, it gets some updated value or numbers. Towards the end, you have a final number or final vector that's assigned to the last token. And we want to take a look at what does that last token represent. We would hope through the training process, the internal calculation is one such that the final distribution over the predicting of the word vocabulary is one such that the correct next word is assigned high probability. And of course, this is done by the very familiar softmax activation towards the end and cross-entropy loss, right? Because predicting a next token, a next word in a vocabulary, that's exactly 1 out of vocabulary size multi-class classification. Does that whole pipeline make sense? Make sense? Great. OK, cool. So towards that, if we think about the distinction that I called out in how attention layer does this sort of horizontal word-by-word passing around information, it might be helpful to look at this example of the word mole. Right? So we see that there are 3 sentences. American shoe mole, 1 mole of carbon dioxide, take a biopsy of the mole. So all 3 sentences would have this word mole. If we take a look at the input embedding step, the step that maps raw words into vector representations, well, then all 3 of them, by this fixed downloaded language model that we got from the internet, all 3 modes would be mapped into the same representation. Well, because that direction in the d-dimensional space would just represent the generic meaning of the word mole. So the magic or the heavy lifting done by attention is exactly one such that I will look around the surrounding words, because the surrounding words is one such that I can look up context or look up meaning. And I would try to soak in the surrounding words' contribution such that I could drag this generic representation of mo into a location or into a direction that is more specific to the sentence. And in order to do this dragging around, there's no other way to achieve this rather than just looking at all the sentences or all the words surrounding the word mo. So this dragging around idea is very intuitive and also the most powerful bit in how we could make use of attention mechanism to do some context-aware a next word prediction or representation updating. So now let's go back to this overall architecture and try to plot things out in a 2D diagram way, so then we can label things and point at stuff. So suppose I have this word, right? To date, the cleverest person, cleverest thinker, and throughout the majority of today's discussion, I'm just gonna pretend that my feature has 4 words. So in other words, I would have an n that equals 4. I have 4 words. I'm passing these 4 words into my whole big black box of transformer. My goal is such that, after the whole business done by transformer, some internal representation dragged around, towards the end, I'm going to produce, for each of these 4 tokens, a distribution over the vocabulary. And my goal is such that some internal weight, internal mechanism is well-trained enough such that for the updated representation corresponding to the word to, this distribution is one such that the probability assigned to the correct next word date is high. Similarly, vertically, if we take a look at the transformed representation for the second word date, I would hope that the final distribution over vocabulary assigns a high probability to the correct next word the. And similarly for the and cleverest pair and cleverest and thinker pair. If we then take open up this whole transformers blocks, right? So we have word in, dictionary over, vocabulary out. Then we see the same pattern that we saw from the animation where, we first turn these raw words into some vector embeddings or the input embedding, the tokenization step that maps raw words into vectors. Then these bunch of vectors that all live in that d-dimensional space is going to be transformed block by block, all together with capital L blocks, such that towards the end we do the reverse mapping and turn vector representations back to words. There are L such transformer blocks, and throughout each block, the input are all d-dimensional, so they all originate from this d-dimensional input embedding, and block by block, we're just doing this dragging around business, right? So they come in as d-dimensional sequence of d-dimensional tokens or d-dimensional vectors, block by block, through the magic of whatever, soaking in context, their representation changes direction in the shared d-dimensional space, such that the end result for the representation that correspond to the original words would all be shifted by 1 index, right? So for example, the date vertical pipeline would be such that the representation is dragged towards a direction that encodes the word the. So transformer block by block, we would all live in that word embedding space. And if we open up a transformer block, right, so there are L such blocks, and the input embedding turns words into vectors. The output embedding does the reverse, turns vectors back to words. If we open up a transformer block, and we remember we saw that there are 2 main components. One is the magical attention layer, right, the new thing, the attention layer. One is that thing that we're familiar with from week 6, fully connected feed-forward network, or a multi-layer perceptron. So inside these 2 building blocks, fundamental building blocks, of course, in multi-layer perceptron, as we recall, in the linear layers, we would have some learnable neuron weights followed by some nonlinear activation, such as ReLU. So we would have some usual neuron weights that can change for a given input how the output relationship is going to come out to be, right? So those are the knobs that we could turn. Those are the familiar knobs that we would already know how to turn the weights. in order to achieve some good loss. And what is the pipeline? Well, that's the backpropagation, right? So we have some cross entropy towards the end. We know that by changing the internal weights, the distribution produced by the transformer block is going to change. So that gives us the signal as to how to update those neuron weights. So those we're already familiar with. The new thing comes in the attention layer. So in the attention layer, we're also going to have some learnable weights or learnable parameters. In particular, we're going to have 4 sets of weights that we learn: the WQ, WK, WV, and W0. And at a high level, the way that we could train for these weights are exactly the same mechanism that allowed us to train for neuron weights, which is exactly backpropagation. So similar to how we train filter weights in CNN, how do we train the vanilla neuron weights in feed-forward network, we could also just take a look at how does changing WQ, WK, WV, WO would change the final distribution and then drive or nudge our weights in the direction such that the loss or the final vocabulary distribution is more desirable. So we're not going to spend much time describing how we can do the backpropagation. That is totally just pure gradient descent algebra. We're going to then, on the contrary, try to more closely look at how the forward process works, or in particular, how this WQ, WK, WV, and W0, the learnable weights, assuming that we've learned good such weights, would turn those raw word embeddings into the desirable vocabulary or distribution over vocabulary. So we're going to focus on the forward pass and understand the attention mechanism. And we see that here, for an attention layer, it has 4 sets of weights. I'm going to then further divide this whole box. There are many, many moving pieces in attention layer. It's a whole big black box. We're going to spend the majority of the time actually looking at 3 such weights, WQKV, and sweep the WO all the way towards the end of the lecture. In particular, we're going to look at how WQKV does the heavy lifting, the most important bits in the whole transformer pipeline that turns this word embedding into the so-called query key value projection or projected embeddings. So WQKV, for now, you can just memorize this diagram. There's some X coming in. Those are word embeddings. And there's some learnable weights, assuming well-learned weights, good weights, WQKV. That is going to do some job that's going to turn the words into the query key and value. And the second step is the attention mechanism. Once we have the QKV, query key value, then we're going to do some sort of context-aware merging. So a quick, small summary, right? So we have this input sequence coming in that's turned into a word embedding. Word embedding is a bunch of vectors, a sequence of d-dimensional vectors, tokens. Those tokens are going to be passed around block by block, dragged around in this shared d-dimensional word embedding space. Inside each transformer block, there is this familiar multi-layer perceptron that we're not going to take a closer look at. But then there's this attention layer, which has this mostly 3 steps. We're going to focus on the first 2. First one relies on this well-learned query key value projection matrices. And you see that already. There are some 3 branches of arrow coming down. Second step is the attention mechanism that at a high level does some sort of merging. And then finally, towards the end of the lecture, we're going to talk about what does WO play a role in. So let's now zoom in and really understand this 2-step process, right? So how do we do the projection and how do we do the attention mechanism? So the first step is the query key value projection. And mathematically, it is actually very simple. It really is just a linear transformation or matrix multiplication that turns X into 3 vectors or 3 tokens: a query token, a key token, as you might have already guessed, and a value token. So really, we just have a d-dimensional representation of X, and we multiply them together with some WQ, WK, WV to give us QKV. So a few questions would immediately arise, I guess. Well, 1, why do we bother if we already have a good embedding, a good vector representation of X? Why do we bother creating 3 copies or 3 versions of this X, right? So what's the deal with this It looks like a trident, although you could also think of it as like the trinity of this vector x, right? Originates from the same x. Why do we bother creating 3 versions of it? Well, towards that, then maybe let's make an analogy. So think of each of us as a word, right? So we are all here in this classroom. We have a bunch of people here. Each one of us, we can think of ourselves as an X, and we're trying to maybe learn from each other. Well, this X would just be our whole personality or whole profile. So X might describe my age, my gender, everything about me, my interest, my personal life, my professional life. But in order to soak in context, well, the context here would be we're trying to learn machine learning. So if you want to learn machine learning, for example, from me, well, then the type of contribution that you want me to give you would have very little to do with, say, my personal life or my sport or my interest or my skills outside machine learning. In other words, you might just want to ask a question and ask me, okay, Shen, how much do you know about linear algebra? Because that's the context-dependent or context-aware question to ask. You wouldn't want to just take in the whole personal profile of me, but rather you want to first get a sense of what type of questions you should ask. And me, from my perspective, I might generate a bunch of keys. Okay, what's my strength? Am I better with linear algebra? Am I better with algorithmic thinking? Am I better with programming? Those would be the keys that I generate, which is a slice of me, slice of my X profile instead of the whole me. And in order to soak in each other's contribution, when you ask me a question about machine learning, I don't give away my whole profile to you, but rather I just contribute by speaking out things that are relevant about machine learning or linear algebra or programming. So in other words, this X splits out into 3 pieces because, well, oftentimes in order to soak in context, we do not need the generic vector representation of the word, but rather the context-relevant questions, context-relevant keys to compare the question similarities with, and the context-dependent or context-aware values to contribute to the conversation. So you can think of query as, okay, your skill set, a key, my internal understanding of my skill set and value, for example, my notes or my slides. So that's my contribution. So at a high level, we would want to map the X, the whole raw word embedding, into 3 small splits, such that one is responsible to ask language processing specific type of questions. One is responsible for listening. Okay, so you ask a question, I listen, and then I do this sort of comparison, and one is responsible for giving an answer. And this WQ, WK, WV, you can think of it as I might have a rich personality, hopefully. I might have a very interesting personal profile that is very high-dimensional, that lives in that D-dimensional space. You think of me as a word. I live in the high-dimensional space. But in order to process a sentence-specific processing, maybe not all of D is going to be relevant, but rather I'm going to have this so-called query key value embedding space. That is dk dimensional. We're going to see another dimension, the dk dimensional space. And the relationship between the d-dimensional space and dk dimensional space is facilitated by these learnable weights, WQ, WK, WV. So in other words, you could also think of these learnable weights as maybe a camera angle, right? So here you take a picture, maybe you can take a 3D scan of the whole profile of me, but in order to take a snapshot of a particular skill of mine, maybe just look at me from a particular angle, maybe from the technical angle. So that WQ, WK, WV are exactly the learned way of phrasing a good question, phrasing a good response, or giving out a good value. So more precisely, or more concretely, when a sequence of word comes in, the learned weights, WQKV, is going to be applied for each and every one of those word embeddings, such that for the first word, I create the first set of QKV triplet. Then for the second word, look closely, it's the same set of WK, WV that is going to be multiplied by the second token, such that, or the second input word, such that it creates the second set of QKV triplet. And it's, again, the same learned WQWKWV that's going to be multiplied with the d-dimensional word embedding vector x into dk-dimensional query key values, and so on and so forth. So why do we share this WQWKWV? Again, using the analogy of camera angle or trying to learn how to phrase a good question. Once you've learned how to phrase a question eloquently, that is a skill that's very reusable, right? So once you understand how to phrase a good question, you could use the same thinking process or the same thinking perspective, the same way of framing your question to different words. So the same WQKV is now going to project a whole d-dimensional space into a dk-dimensional or 3 dk-dimensional spaces. So instead of just word-by-word mapping, it's a space-to-space mapping done by this WQWKWV. So with all of these, right, so all 3 weights, WQWKWV, are the learned way of phrasing your question, tuning your listening skills, and framing how you should respond or contribute to make the conversation flow. So WQKV, WQWKWV, they are all d by dk dimensional learnable matrices, such that we turn some d-dimensional word embedding into dk dimensional query key value embedding. We see that the projection is done by this set of WQKVs, and in practice, dk, the QKV embedding, is relatively much smaller than d. Here's another sort of intuition, right? So when we are trying to reason about word, as we mentioned, this d-dimensional word embedding space, that has to capture all the nuances of raw English language. And we argued that, well, maybe in order to process a sentence, we don't need to take a look at the whole profile, the whole entirety of a person's X or a word's X, but rather we just want to get a glimpse of the task-relevant questions to ask, task-relevant contributions, task-relevant answers or responses. Those all live in this dk-dimensional space. And dk intuitively would be much smaller than d because, well, maybe I just have a smaller abstract space where I do this sort of thinking. Right? So when we speak out loud or when we project ourselves in the whole world, well, maybe my personality is very rich, but whenever I process a particular question, I try to do some sort of internal processing. You can think of this d as a real dimension, dk as some sort of internal understanding, internal processing dimension. So we would do this similarity or semantic comparison in this dk dimensional, much smaller space. And for reference, for example, GPT-2, the d would be 768. A dk typically is a 16 or some number that's at the order of 20. So dk is much smaller. And very importantly, it's the same set of WQWKWV that is applied through the whole sequence of the words. Because, well, this W, they are not just some abstract learnable weights. We interpret them as the projection matrices that maps the raw word embedding space into some meaningful question space, answer space, response space, query key value spaces. So it's the same WQKV shared along the whole sequence. So very importantly, one of the reasons, we'll see maybe towards the end, that transformers really took over language processing is, one piece is already shown on the slide here, is that this mechanism, this machine, does its processing in a parallel and identical, structurally identical fashion, right? So regardless of how many words you give me, I have this WQWKWV that is just going to be multiplied with each and every one of your input word. In other words, you give me a raw word, some downloaded model turns that into a raw word embedding representation. Once I've learned how to ask questions and respond and listen, well, those skills are just going to be applied throughout the whole sequence. And that is very efficient because, well, in this whole layer, regardless of how long your sentence is, I really just have these 3 ways, 3 framings, 3 perspectives, 3 lengths through which I look at the whole English language. Does that make sense? Doesn't that make sense? It's the same WQWKWV. Very good. Okay, so now Once we understand the role played by the learnable weights W, Q, W, K, W, V, which, by the way, eventually you will see, well, the whole business of transformer is really just a learnable way of asking and listen and answer in this tunable way to achieve some desirable distribution. So once we have this W, Q, K, V, we do the linear mapping such that the word embedding X, the whole sequence, is going to be turned into a sequence of query key values. And that reminds you of the soft dictionary lookup example we saw previously. And exactly the role played by query key value and the attention mechanism is such that after the attention mechanism, we're going to be able to create a sequence of the so-called Z vectors or Z tokens. Yes, here yet another symbol. So we're going to introduce so many notations and so many different symbols in transformer. There is powerful, but then also very complicated. So we're going to use this attention mechanism to turn this sequence of X, which gave us a sequence of query key value, into a sequence of Z. So what are these Zs? These Zs are exactly the context-aware, transformed or merged version of X. So these Zs, as we will see, they are just a mixture of everyone's value weighted by how relevant that particular response is with respect to the question that I'm asking. So that should remind you of that whatever 0.1 banana, 0.1 apple thing, right? So we would want to turn some raw representation into a representation that merges everyone's value in a sensible way. And those are encoded in these Zs. So let's then really dive in and take a look at the attention mechanism. Once we understand the high-level story, well, the good news is attention mechanism isn't that complicated. Well, in particular, we already understand that, well, there's a bunch of words. To date, the cleverest, those words are turned into those axes, those d-dimensional word embedding vectors. So there are three arrows that trident down this trinity of QKV. Those are the internal thinking process that we frame our question, that we listen to each other's questions, and we respond or contribute by giving out values. So those QKVs, they live in dk-dimensional space. So where does this attention mechanism come in to turn those X sequence into the Z sequence? So the first step would be, well, the first word, to, once we've learned how to ask a good question through the learnable weights WQ, and which give us this Q1, the first query. Then the first query is going to then ask a question or broadcast, or think of it as me. I'm X1. I have my personal profile. I want to understand your personality, or, for example, I want to learn the snowboarding. Okay, so in order to learn from this whole sequence of all of our X's, I might broadcast out a question. So Q1 would be my question. My question would be, who here is good at snowboarding? Each one of you might have an internal key that encodes, for example, a whole sequence of your skill level for different sports. And if there's anyone here who has a strong skill in snowboarding, then my question is going to have a high response or high similarity to your particular key. And that is encoded in this query compared with different people's key dot product similarity idea that we already discussed. Right? So I ask a question. That question is specific to me. I broadcast my question. I compare my question with everyone's key to see who among all of us would have the highest response to me. The highest response is encoded in this dot product similarity. And I'm going to then apply the softmax idea to turn these raw dot product similarity into a distribution, into some percentages. And as you might have already thought ahead, those percentages are then going to be used to merge together values. But before we get there, though, there's one additional small step that you would see in practice. People would do this dot product similarity, but then they would scale down. They would divide this whole sequence of dot product similarity by this square root of dk. Not too important, but the gist of the idea is just that when we have a long vector, when we have a high dimensional vector, And when we do this dot product, we would have to add up dk number of pairwise scalar multiplication product, right? So it's the inner product, the dot product. So when dk goes somewhat big, reasonably large, then we have to add up a bunch of numbers. And those numbers would saturate softmax in the same way that, for example, sigmoid would saturate when your input is towards the infinity region. When your input goes bigger and bigger, sigmoid would saturate, and since softmax is a generalization of sigmoid, softmax would also saturate. And then people would divide the whole dot product sequence by a square root of dk just so that we have some good, meaningful gradient flowing back to the training process. So not that important, but then practically it is always implemented in that way. We divide down by a square root of dk. So this step would then give us the so-called softmaxed attention scores. And these attention scores would then be used to multiply or merge together all the values. Right, so we have, because in our example, we have a sequence of 4 words. We have a 4 dot product similarity when we anchor our focus on the first token, right? So in order to get a sense of the word to, how to transform the word embedding for the first word to, the word to asks the first question. It's the same question broadcast and compared with everyone's keys. Those dot product similarity scaled down for numerical reasons is going to then go through a softmax to give us this percentages. Right? A softmax output is a distribution. So those percentages are then going to be used. So those percentages, again, similar to the 0.1, 0.8 contrived numbers. So those are the sensible, context-aware relevance percentages that we would then use to merge together all the values. Then similarly, right, so then maybe we move on to the second token. We would have to think about how we can transform the generic embedding for the word date into one that hopefully towards the end is closer to the embedding for the word the. So how do we do that? Well, then the second word is going to come up with a question that's encoded in query 2. Query 2 broadcasts through the whole sequence, compare dot product similarity, and by scaling down for numerical reasons, we apply a softmax to get us this attention score or the softmax percentages to then multiply together all the values. You have a question? Not yet. So query matrix is a different thing. We're going to get to query matrix in a little bit. So far, there's no matrix for query yet. So the only matrix are the projection matrices. So far, we've only talked about, right? So far, X, Q, K, V, individually, they are all tokens or all vectors. So X are in D-dimensional space. Q, K, V, they are all in DK-dimensional space. The only matrices we've mentioned are the WQ, WK, WV that maps query key, maps X into query key value. We're going to later see a query matrix, but that's a different thing. Yes, very good. Yes, WQ, WK, WV, they are the same W shared by the whole sequence. And of course, QKVs are going to be different, right? Why? Because, well, X are different, right? So it's the same WQ that's being multiplied with X1 that gives us Q1. And it's the same WQ that's multiplied with a potentially different X2 that would lead to a different Q2. So analogy would be, well, in terms of asking about snowboarding, the way that I phrase the snowboarding question might not be exactly word by word identical to the way that you phrase your question about snowboarding, even though the projection of mapping whatever me into a snowboarding relevant question, that projection, the camera lens is the same. Our shadows might not be different, might not be identical because you and I are different. Does that make sense? Does that make sense? Right? So I'm an X1, you're an X2. We're different axes, so by looking at us from the same angle, the projected shadow are going to be different. Then that's your Q2, that's my Q1. But then your Q2 is going to then be compared with each and everyone's key to, again, do this similarity comparison and then turn that through a softmax into some percentages. So those A's, those attention scores, softmax attention scores, those exactly captures sort of relevance. So for example, A21, that exactly describes how much attention in order to update the internal representation for the second token, X2, should I pay to the first token, right? A21. That is how much attention, how much relevance is the first token's contribution going to be towards updating the second token's representation. Does it make sense? Oh, cool, good, verbal one. Okay, great, right? So that is how we update the second token's representation. Then, okay, I'm going to skip a little. Let's maybe think about how do I update token 4. So hopefully now you get a small grasp of this, right? So again, question, token 4 wants to get updated. Then it's token 4's job to ask the question. So query 4 is going to then be broadcast to the whole classroom. Query 4 is going to be then compared with everyone's key for the similarity, for the numerical stability, for the softmax to turn into a bunch of percentages. So for example, A43 would encode the percentages or how much attention should the fourth token pay to the third token in order to update its internal representation. So the gist or the punch or the twist of the story is, well, why did I go to token 4 in order to update token 4? Well, we realized that, well, this is actually yet another parallel and structurally identical processing, right? So in order to update my representation for token 4, I didn't actually have to wait for token 3 to be processed. In order to get Z4, I didn't have to wait to get a Z3 first. So all of these can happen parallelly. So we already saw one parallelization, which is it's the same WQ, WK, WV that's being multiplied with each one of those tokens. Here's yet another identical processing, which is all of these tokens are going to follow the same structure. So no, token 4 is just the fourth token, ask a question, compare that with all the keys, get the similarity scores, similarity percentages, then do the weighted sum of everyone's contribution, everyone's snowboarding skill, everyone's values. Those are going to be my updated representation for token 4. But then I could then maybe go back to question 3 or token 3. Then it's yet again the same process. Token 3 asks a question to everyone, compares dot product similarity, scale down for numerical stability, softmax to give me some reasonable merging percentages, and use those attention merging percentages to actually merge together all the values. Does that make sense? So it's the same thing, right? So and then the parallelism is just that I didn't have to wait for one word to be processed in order to process the next word, similar to how I could learn about snowboarding without each one of you have learned snowboarding already. Yes, question? Right, so values would be, for example, in the analogy, value would be the particular trick I would teach you about snowboarding, right? So for example, I would tell you, oh, use your core, and then, and then you would realize, oh, I don't have a core. Things like that, right? So it's yet another glimpse of me, right? So I am a full person, but in terms of learning about snowboarding, it only has to do with the physical part of me. So those are the values. Or in the earlier analogy of learning about, say, linear algebra or machine learning, the values would be, say, your notes, your slides, your books, things that you sort of produce that's relevant to making the contribution. So this whole pipeline of turning some sequence of X into a sequence of Z, those are the so-called attention head, right? So if you recall, we mentioned that there are two main steps: the mapping of the sequence of input token X, word embedding X into Z's by this learned query key value projection, and then the merging that's done in the attention mechanism. Very importantly, it's parallel and structurally identical processing. Now, back to Shinka's earlier question about query matrix. Actually, yes, nice segue. So this whole picture of doing things one token at a time, actually, once we get comfortable with thinking about this whole pipeline, well, you will see that you can also just more compactly represent the whole mechanism. There's no new math whatsoever. It's just a different way of assemble all the math. We could actually stack the whole sequence of whatever. There's a sequence of X, there's a sequence of queries, sequence of keys, sequence of values. There's a whole sequence of n objects in respective categories. If we just stack all the n number of stuff vertically or in terms of row stack, then we could get ourselves a compact representation that might also be helpful to hammer down this query key value business one more time. That turns this pipeline that's vertical from X to Z correspondence to this almost look like an Apple Vision Pro type of diagram, right? So where you would have this more compact capital X, capital Q, capital K, capital V, capital A, capital everything. So how does this capital thing work? Well, this capital thing is really just an assembly of all these small letters. So in particular, we have a sequence of words. Each word is a d-dimensional word embedding word vector. So we can stack them all together to form ourselves an n by d, which again is hopefully familiar because we always deal with X that's n by d. So that's kind of fortunate. So we have an X that is n by d. Well, through this learnable projection WQ, we can get ourselves a bunch of queries, one for each of the input token. But written more compactly, we can now have this query matrix. Query matrix is just a row stack of each individual token's query representation. So you can reason or argue about the shape. So query matrix will be n by dk. Similarly, because the projection matrices, they all live from mapping d-dimensional stuff to dk-dimensional stuff. All the projection matrices are d by dk. So the resulting query matrix, key matrix, and value matrix, they all live in n by dk. So there are n such vectors, such tokens. Each of these n tokens live in this, each of these n tokens live in this dk dimensional space. In this picture, in this cartoon visualization, dk is just 3. Right? So each of the d-dimensional X tokens is being mapped into a query token, a key token, a value token. They all stack together. So what are the steps that we went through? Well, we talked about how we compare each query's representation with everyone's keys. So that is the dot product similarity. So compare query I with key J, with key J or KJ, so that, since there are n queries, one for each input token, and n keys, one for each input token, we have n squared pairwise dot product similarity. And that could help us assemble an n by n dot product similarities, whereby, for example, this entry would be this first row, third column would be the first token's query compared with the third token's key. And similarly, this entry would be the third token's query compared with the fourth token's key. Right? So there's this n by n matrix where the row index correspond to the query, who is asking the question, and the column index, the J's, correspond to the keys. So one idea that I saw when I first learned about this, since there are so many moving pieces, I got myself confused about all the indices. The one idea that might be helpful when we talk about this QK multiplied together, that we have n squared elements, well, you might think of it as, well, which index talks about query, which index talks about the key. I is the index that typically talks about row, and J is the column. So how do we memorize this? My trick was that, I am a curious person. I ask good questions, so I is the query. And key, well, the keys can jiggle, so K correspond to the J. So J, the column index is corresponding to the key. So now you can, when you have this n by n matrix, right? So Y is n4 because we have 4 words. When we have this n by n matrix, the ith row, jth column would correspond to how much attention should the ith input pay to the jth input. Does that make sense? You had a question earlier. No. You had a Yep. So there's a convention of the curious eye jiggle key. So I can assemble all of these n by n entries into this raw dot product similarity. And as you recall, raw dot similarity, what do we do next? Scale down by square root of dk for numerical reasons. Apply softmax on each row because that's applied for every given query. Right? So I have 100% attention in quota. I want to distribute that towards every one of us. And that softmax helps me turn my attention into a distribution or into some attention scores, softmax attention scores, A11, A12, all the way to A14, such that each row sums up to 1, sums up to 100. And that is the row, or that is the percentages that I would use to merge the values in order to update my internal representation, right? So then the attention mechanism or the attention scores is going to be then multiplied with the V's, with the values, to soak in everyone's, say, snowboarding trick notes and so on, to update your internal representation. And that is the Z. So more compactly, you could even, sometimes you even see that, well, in a diagram, in a real paper, people would actually visualize the whole attention mechanism just using this many symbols. So hide away a lot of the mechanism, right? So there's this X comes in. X is going to be mapped into some query key value. Query key value then does some very weird, hairy mashing in the attention mechanism. Towards the end, the attention mechanism spits out a Z, an updated internal representation for the word. And then that applies for the whole sequence. Does this whole idea make sense? Make sense? Right, so this is just stack together a bunch of stuff in a row-wise fashion. And then you have this, instead of attention scores all come in scalar form, then you have an attention matrix. So one more time, drive this point home again, right? So we have this now two-way of thinking about attention mechanism, a vector way and a matrix way. So here, when we think about the attention matrix, important to realize now, right? So the attention scores, they really only depend on the query and key, or more precisely, the dot product similarity scaled down by square root of dk and applied on top of it a softmax. So attention scores only depend on query and key, and in particular, for the first row of the attention matrix, which is responsible for telling query 1 how much attention should you pay to each one of those 4 keys. Well, that entry, that whole row, only has contribution coming in from query 1 and other keys. So pay attention to all the gray out bits. Those are irrelevant to the discussion, right? So when we talk about the first row, only query 1 and key 1 to 4 is relevant. And in updating the representation, then value comes in, right? So value would come in order to give us this relevance weighted merging of the values to give us the Z. So Z1 in particular is just the first row, multiply each one of those scalar percentages multiplied with the values. And since all the A's, A11, A12, all the way to A14, they are scalars, and all the V's are in dk dimensional. This Z1 is in a dk dimensional, Z2 is a dk dimensional. Again, pay attention to all the highlighted colors, right? So in updating for Z2, what are the relevant bits? Everyone's keys matter, everyone's values matter, but in updating X2, only Q2 matters. Because, well, I don't care about what type of questions you each ask. I only care about my question. I only care about your key. I only care about your values. Similarly, Z3 and Z4. Make sense? Any questions? OK, then maybe let's take, we're slightly pressed for time, maybe 2 minutes of a break before we talk about multi-headed attention.
I understand why we need Q and K.
Okay, we need Q and K to compare similarity. But then how are you gonna be better at snowboarding, for example? From just, okay, query and key, it tells you who you should learn from. but learn what from that person. For example, okay. Say, you want to learn, so, okay, skateboarding, say skateboarding, I'm good at skateboarding. So you ask skateboarding, I say, okay, I'm terrific in skateboarding. Okay, another reason could be, hey, in order to learn from me, you actually have to see me do some trick. Either to pick up some skills or maybe call my bluff, something like that. So that type of demonstration that I would do for you, that's the value. Because you can actually just learn from the values. Similarly, if you call back the analogy we had from English to French, right? So English to French, there's that whatever similarity. So then the fruitness, the semantic gives you the idea of 10%, 10%, 80%. But in order to give somewhat of a merging in French word, then those values had to come from some French representation. So if you recall from the fruit example, the values that we merged together are the French translations from the fixed dictionary.
Yeah. Those are the values.
Those are the values, right? So queries and keys, they just tell you how much attention to pay to everyone. But then the values are actually what helps you to update.
Okay, the values are kind of like a basis, vector basis.
Very true. Yeah, I would agree. So because, so think of, updating a vector in, the basis would tell you which direction to drag to.
But then all the values are different for each x.
Yes, everyone's values will be different.
Okay, I see. That makes sense.
Cool. Okay. Let's see, is it 2 minutes? Actually 3 minutes. Okay. Let's continue. So next up, we're going to talk about generalization. So as if attention isn't complicated enough, as if we haven't seen enough symbols and ladders. Actually, I think the first time I taught transformers, I was like, okay, I didn't realize that sometimes the small ladder and big ladder, they represent completely different things. And I was like, I used to think in calculus class, Greek ladders will give me enough trouble because, anyhow, enough of putting down transformers' arbitrariness. But, from attention mechanism, which tells us how to do this context-aware merging or updating, we can generalize the idea to multi-head attention because, understanding language, typically, you cannot just pay attention to one aspect of the whole sentence. For example, I might have learned through my learnable weights WQ to ask a question about, hey, which one of you is a noun, right? Because, for example, the type of word, what type of word are you? That's very important in language processing. But then nounness, adjectiveness, or the properties of those words, that's just a glimpse of language processing. There are many other aspects in language processing that could help us figuring out how much attention to pay to each one of those words. For example, things like tense, things like gender, if the language supports it, things like the tone, right? So there are many different ways we could interact or learn from each other. For instance, even if I just want to learn about snowboarding, I might just ask you, maybe go back to the core joke, which one of you have a good core exercise drill? Things like that. So in order to, what happened to my value 4? Okay. Sad. Maybe I deleted it by accident. There should be a value 4 there. Sad. So there could be that is a token that has no intrinsic value. Sad. So we could pay attention by learn about one way. Now you see my WQ, WK, they now have superscript, right? So those superscript now encodes one aspect that I could learn about how to pay attention. So I could then maybe come up with a different so-called attention head, which, with the superscript 2 encodes another aspect that I've learned to phrase questions, to respond to questions, to listen to questions, to contribute to the conversation. And I could continue on, where each head would be responsible to figure out one aspect of language processing, very much like that three-headed dog in Harry Potter, right? So you have 3 heads, then you can pay attention to different perspectives of the environment. One hat might be responsible to pay attention to, as we mentioned, gender. One hat might be paying attention to, different skills that's relevant. But then you could continue going on like this, sort of orthogonal to this whole sequence direction, whereby each hat would have its own WQ, WK, WV, which intuitively can be interpreted as each hat has learned its own angle to look at the world or to shadow a whole persona into some decay-dimensional space. So we could have all of these copies or slices of attention hat, whereby we could assemble this so-called multi-hat attention. And well, this whole pattern of parallel and identically structured processing would come up again, whereby we see that, well, the processing is parallel and structurally identical across all hats and all tokens. So there are two directions involved here. So here, or going into the slide, this is the index along the hats, right? So each cut here would give me a hat. And in each hat, we see that, well, in each hat, we learn its own projection matrices. We learn the own way of phrasing a question. So learn its own WQKV. It would create then independent in that particular sliced hat. I would then use the hat specific WQ, WK, WV to create QKV. And then this specific hat then parallel, there's no back and forth translation or back and forth communication, right? So then inside this whole slice, the QKV sequence is then going to be turned into a sequence, the context-aware sequence of Z. But then it's also structurally identical. For each hat, the way that I process the first hat is exactly the same as the way that I will process the second hat. It's just the first hat and second hat would have different projections. So the numbers are different, but the number crunching mechanism are exactly the same. So this is along the hat direction if we slice things this way. But then if we take a look at this direction, this horizontal direction, which goes along the sequence, then that's the first part that we discussed, right? So for each token, it's the same WQ for a given hat. It's the same WQ that's multiplied with token 1, token 2, token 3, first word, second word, third word. So along the tokens or sequences direction, it's also parallel and structurally identical processing for each token. So altogether, this is just a big parallel processing machine, right? Of course, the parallelism is just in terms of processing. It's not that everyone is just its own machine. For updating my query or for updating my token 1 or for updating the first word, there is sort of a neighboring chattering, and that neighboring chattering happens inside each individual attention hat's attention mechanism, right? So I do learn from everyone. It's just that the way that I'm learned from everyone doesn't depend on the way that each and every one of you, how you learn, right? So you can learn at your pace. I could learn at my pace. It's just that we're going to follow the same number crunching formula to learn. Does that make sense? Similar to how there are you here in this classroom doing this live lecture, there are maybe other people who's watching the lecture recording, but then it's the parallel processing, but then maybe we would all learn from each other's questions. For example, you might ask a question here, that would be your query. Then I might give an answer that would be my value. And why did I give an answer? Maybe because my key corresponded most strongly with your question. So that updated your internal understanding. But then you might also learn from each other. For example, someone asked a question on Piazza. But the gist of the parallel and structurally identical processing is that, well, how we learn are the same, but we don't have to wait for each other to finish learning in order to do our own learning. Does that make sense? Very good, right? So this is exactly multi-hat attention. So basically, do the attention hat multiple times. In particular, we're going to do this capital H times. So yet another ladder. So H, capital H, just means how many hats are we going to have? And each head is going to produce its own sequence of context-aware z's. So now we have to assemble all of these z's coming from each individual head in some way. And somewhat arbitrarily, we're just going to concatenate them together in order to give us the sort of multi-head, context-aware, transformed internal representation for the first token is now going to be called Z1. So this is a whole concatenation. And then similarly, for the second token, we concatenate all the heads contribution. Again, parallel identically than Z1 and Z4. So each of these multi-head concatenated Zi is going to then live in this dimensional space. And for each one of these Zi's, Z subscript I, subscript correspond to the token index, then that's where the final WO that we haven't talked about comes in. So once we have done this projection, attention merging from an individual head and then a bunch of heads concatenated together, we then cap everything together with a so-called attention output projection that just maps, yet another linear projection that just maps all of these Z's into the so-called Z outs. And these Z outs are exactly the overall input-output of a whole multi-head transformer's attention layer. So some X comes in, these Z's are back in the D-dimensional space through this back and forth from D to dk, then capital H times dk, then back to D. Just a bunch of linear mappings throughout, such that in the end, the end-to-end relationship in a multi-head attention layer is just a word embedding X that is going to become another representation that's Z out. And those Z out have the context awareness. So if we summarize everything, it might be helpful to walk through this shape example. So what are the important bits? Well, suppose I have 5 words, different from the cartoon that we've seen so far, right? So in the cartoon, we always have 4 words. Suppose now I have 5 words. Somehow my word embedding is 6-dimensional. Then all the shapes that we have encountered today are dumped onto one single slide. So first, I would have an input sequence that is M by D, and then I would have a dk-dimensional embedding. By the way, D and dk, as you might have guessed from the GPT story, those are the hyperparameters that you get to choose, similar to the number of neurons, similar to how strong or how rich you want your representation to be. You pick those numbers. So D and dk would give us the dimension, or dictate to us the dimensionality for a query projection matrix, for a key projection matrix, for a value projection matrix, for a particular head. And those projection matrices are then going to produce for us a query matrix, a key matrix, a value matrix, whereby query matrix and key matrix, they together would be responsible to create attention matrix. Then attention matrix is going to be multiplied with the value matrix to give us the attention head output. And all of these happen inside a single attention head. And you could then, towards the second part of the lecture, we talked about how you can have different heads. Those different heads would be denoted by capital H. So in different heads, then you would concatenate all of individual heads' attention head output in this very arbitrary stacking way to get this multi-head output. Then through the learnable ways of an output projection, we get this final Z out. So importantly, if we zoom out and think about this whole pipeline, we see that X comes in as an M by D, and Z out, the final output of a multi-head attention layer, is an M by D. So it's the whole internal mechanism that dragged from the mode, the generic mode, into a different direction in the same D-dimensional space for this particular value X. Does it make sense? Does the whole shape thing business, right? So all the symbols, all the shapes, all the numbers that we have looked at. And importantly, through this whole pipeline, the green parts are the learnable weights. We learn to phrase questions, learn to listen, learn to respond. And finally, we learn to map all the context-aware Z's. back into a word embedding space, or sort of group together all the processing that happened in our head in our dk-dimensional space into the real d-dimensional space, or verbalize our thinking process. So that's the job done by WO, capital O. So with that, that's the gist of transformers, and we will see in lab and in homework there are some other bits that is going to make the autoregressive transformer training pretty successful. Ideas like positional encoding, ideas like masking, those are also very important. I would say appendix, they would be indispensable, but they wouldn't fit into the overall narrative of transformer. They are sort of a trick that's specific in training language models in this next token prediction way. We're going to see the details of that in the lab. And here's another visualization. I'm just including that for reference in case you want to validate your understanding of transformers. So with the remaining time, let's maybe talk about how people are now using transformers, or some of the applications. So one, I guess, this will be full disclosure. Well, the transformers architecture, as some of you might know, it came about a few years ago. And when it actually first came out, people were not so gaga about it because, well, the empirical result was very good, but nobody really understood why did we have to do all of those whatever, merging whatever value. And in fact, for confession, I actually had to cook up a lot of analogies in order to make sense of all the arbitrary math. Because in the early days, transformers were really understood as a way of doing we all know SGD, right? Stochastic gradient descent. People used to think of transformer as GSD, graduate student descent. Basically, a graduate student tries a bunch of stuff and see which one works. And transformer turns out to be the one that emerged from a bunch of ideas that they tried and then worked. But then later, people realized actually there's some nice things about transformer that make sense of this whole sort of merging idea. For example, well, empirically, you can already see transformers is now kind of one architecture that rules them all. We used to say CNNs is the de facto architecture for images. Now, even for pure image processing tasks, transformers are outperforming CNNs. And one of the niceties about transformer has to do with both this sort of nice property of tokenization. Basically, because transformer is just processing a bunch of tokens in this sort of parallel and structurally identical way, we could apply this transformer idea to any number of data structures. So for images, you could chop up a bunch of images into patches, and then each small patch is going to become a token. Then it's the same architecture that can look around surrounding patches, which is a sensible thing to do in order to make image processing tasks successful. Similarly, for audio processing, chop up a bunch of waveform into bits. And because this transformer idea of learning about a representation in some shared space, it really opened up applications such as multimodal reasoning. For instance, if we want to ask a question about an image, we could very much think about the patches that comes from the image as the values, or as the sort of the contribution, whereby the question that I want to ask, well, maybe those would be the query. If I can somehow create a shared embedding space query key value, then I could compare one modality with another modality in order to calculate the cross-modality attention or cross-modality similarity. That already, you actually sort of see that in Lab 8, right? So in Lab 8, when we talked about, when we showed how this text encoder and image encoder, they could be trained in order to sort of push paired or corresponding pairs to have similar embeddings. That also drives or hinges on having this good representation that is shared across different modalities. And since it's the same transformer that does the processing, it's very efficient that two modalities can be processed similarly. One other nice thing about transformer has to do with the attention mechanism. People have started applying the transformer architecture on different applications and realized, for example, in biology, they actually learned that, just give the transformers a bunch of unlabeled data. And by looking at which part of the whole sequence, or for example, there's a sequence of molecules in, which part is this molecule paying most attention to? Well, from that interpretation, actually, transformers does show scientists that, there's some unknown contact that emerged from just reading which part is the most relevant in getting some good unsupervised learning results. Similarly, people have also compared attention mechanism or attention matrix, which one has the highest response, compared with human brain MRI scan. And notice that transformers actually allocate, in processing language, transformers would allocate attention in a way that's analogous to how humans would pay attention to different pieces of the words. Similarly, people would now try to cursed or move their mouse onto this video to see, in order to do tasks like scene segmentation, if I move my mouth to one object of this whole scene, which part of the different patches would be the piece that my reasoning pays most attention to. And you see that very naturally this kind of segmentation emerged out of the attention. Similar idea emerges from, say, image captioning, right? So when we do this image captioning, you could then fix your transformers and see, okay, I mouse together all these words, and I want to understand in predicting or in making this Frisbee prediction caption, which part of the input patch was the part that I paid most attention to. And this would be the so-called success mode, although this would be a failure mode. I guess we could also maybe forgive the transformer because, well, this piece that the transformers architecture paid most attention to, that does look somewhat like pizza, and this does somewhat look like, this one does look like a giraffe, does look like a bird. So I'm going to end on a particularly interesting case, which is, I think in 2023, when Transformers was, around the same time ChatGPT was making a wave, people are basically pranking large language models all in different directions. So one thing that they notice is that, well, it seems Transformers and all of these multimodality models have learned its internal language. In particular, if you put in this whole nonsense, it doesn't mean anything in English. If you put that into the model, consistently, the model is just going to generate a bird image for you. And as if that's not interesting enough, they've gone full circle. They've asked the model to generate an image whereby the whale is talking about food. And the cartoon image generated had this speech bubble. And inside the speech bubble, there's a bunch of yet another nonsense words. And lo and behold, if you put in this nonsense bit back into the model and ask it to generate yet another image, well, it generates images of shrimps and small fishes, which are exactly, indeed, food for whales. So then that opens up a very, a heated discussion about, well, did Transformers actually just learn some self-consistent and coherent representation of the world that's not understandable by us humans, but somehow is intrinsic to the model itself. And maybe, if you further down this philosophical discussion, if Transformers scraping down the internet, evolving and learning on its own, somehow develop its own sense of the world, then eventually what do humans play a role in this whole development? So that's all very interesting discussions. To summarize our discussion today, though, right, so we only just focused on one glimpse of Transformer, which is the mechanical understanding of how to turn the representation block by block through this attention and multi-head attention mechanism. So then we could soak in context and update our internal beliefs. With that, let's finish the lecture. Thank you very much.